Hey guys, I'm Pranay Simpariyar, founder of InfernoRT, and for the better part of the first half of 2026, I've been building an inference engine for large language models to run on constrained memory. And so basically, we started by asking how much intelligence can we basically run inside a fixed resource budget? Because modern models are very capable, and deploying them locally still requires developers to basically reason about the model size, cache, residency, available memory, resource constraints, and um, so it's very difficult to get lost in that mess. And I don't think the developers should have to make all those decisions. And so with Inferno RT, that is the exact problem we are trying to solve. You tell the runtime what resource it has, and the runtime decides what is the best way to use them, right? And so, with that in mind, let's begin. Uh, we can start by checking out what options we've got. All right, so we'll just go through. This is the command line interface, and we'll just go through some of the commands here. We will not go in depth on anything other than run, which is our focus for the day. We'll cover the others in the upcoming sessions. And so, to start off, run is basically a single inference request. You send a request, you send a prompt, and you get a response back. That's about it. Um, you define a couple of things along the way, and but yeah, that is what run is for. Chat creates an ongoing local interactive session, so you can keep chatting and getting a response from your LLM all locally. Serve exposes the model through an HTTP API for applications like Llama or the Llama Studio, so that you can connect, or your own applications, so that you can connect them to your large language models and apply those rules that you set on InfernoRT onto your applications. Bench basically measures workloads and compares runtimes. Um, so that you know when to use InfernoRT and when to use something else. Apart from that, inspect basically lets you examine the models and the memory plan before execution. Doctor checks whether the runtime and its backends are ready, and the model discovers models that are available locally. That being said, we are only going to use run today. So let's begin with like a single inference request. And I'll show you how that looks. Basically, something like this. Now let me walk you through that. The final argument is the local model, which is in our case Meta Llama 3.1 8 billion quantized model. It is a Q4KM. Let's see if you can get to see that. Okay. Yeah, so this is the model that we are using, 8B instruct Q4. And okay, so now that we have that, let's copy this again. Okay, so let me walk you through those. First is memory. You basically define this is probably the most important input. I'm giving the runtime a hard 4 GB memory budget. I'm not telling it how to fit the model, and I don't know how it will fit a 4.6 GB model on a 4 GB RAM. That's not my problem. That is what the runtime is supposed to do. And then I set context, which in this case right now is 4096. This reserves a context capacity of 4096, and we give the option to be flexible with this. You can go as high as you want as long as your model supports it. But right now we are being conservative and picking 4096. Threads, this is basically how many sort of CPU worker threads that we can use. And so that is right now for us 8. Batch size 64 and U batch size 64. These describe the logical and physical batching limits. I'm providing normal workload parameters, not manually describing a paging strategy or a residency plan. What's next? Next is backend is CPU. So this demonstration runs entirely on the CPU. There is no GPU acceleration involved. Even though I'm using a Mac, there is no MLX. So this will be um, running entirely off of CPU. Temperature 0 gives us a deterministic output, which is useful for our live demonstration right now. So that's why I've picked that. Prompt, so this is the actual task. I've picked return only the Kubernetes rollback command because I worked in environments where Kubernetes and was a big deal. So that's why I just picked that. And perf flag, we basically have three for telemetry. We have no perf, we have perf, and then we have debug perf. All of this basically tells InfernoRT how much of the telemetry to expose, how much of the performance telemetry, so we can see what the runtime has decided. Now, what's peculiar about this command is, if you notice in this command, there is no streamed execution, there is no residency window, there is no layer placement configuration, nothing. We've not told any manual offloading plan. I've just described the workload and the resource boundary. Now, InfernoRT is responsible for finding the best legal way to execute it. So let's see how it does that. Now, right off the bat, you can see hot, warm, cold, and evicted. So these are just like tiers that InfernoRT puts its layers into, and so it's basically evaluating the candidate execution strategy. It estimates the memory requirements, and it rejects the candidate that cannot satisfy this budget. Um, and among the candidate that remains legal, it chooses the fastest viable plan. And so now let's go through this result, okay? The strategy that InfernoRT decided on was streamed multi-segment vector. As you can see right here, this is the strategy it went with. It was basically streamed chunk. Um, it was not selected by me. The runtime selected it because the model cannot remain fully resident inside a 4 gigabit RAM slot. So when the answer appears and the request completes within the request memory boundary, uh, you can see that the memory that we used was much under the 4 gigabyte cap that we gave, and we had a speed of 2.84 tokens per second. It's pretty low. We had an end of statement over here for 5 tokens. So, and you can go through all of these basically to understand like how your tokens are being managed here. There were no warm or cold bytes that were used here, but there will be cases when it picks those as well. So we'll probably get to those later. Now let's try something else. Okay. Uh, let's try to force our LLM into giving us a very long response. That way we can see and do a bit of a pressure test and see if we can sustain that. Explain how Kubernetes rolling deployments work in around 150 words. That should be plenty. And one other thing that I would do is give it that range, give that boundary. So now I'm basically changing the workload. Same runtime, same 8 billion parameter model, same machine, same CPU backend, and most critically, the same 4 gigabyte memory budget. So the answer is simply longer. So let's see how it handles that. Okay, so straight away I can see the hot and evicted are different here. This is 3 GB, this is 1.6, and over here we have 2.94 and 1.72. Um, so InfernoRT continues executing through the bounded plan that it selected. Uh, and the developer did not have to recalculate the model's memory requirement or create a new configuration for the longer answers. The runtime basically adapts the execution while preserving the same resource boundary. So that's pretty cool, I think. And so this is again a different different way of showing how InfernoRT works. Right now, it is streaming. You can have like a batch process where it basically gives you all the response all at once. We'll let it finish and then we'll move on to our next experiment, and we'll see how the results look. But basically, right now, how it looks is we we are definitely under our defined memory cap. Let's check that. Let's check that. Okay. Now, okay. We are way under 4 gigabytes. We are somewhere around 3 gigabytes. This we are using VMAP over here. Right. Okay. Ah, did I miss it? Did I miss it? Okay. So it's still going, and since we are running 256 max token command, it might take a bit longer. That is expected. Um, but as you can see, even if it is a bit slower and it's somewhere, um, decode token per second is 1.93 and prompt is 1 tokens per second. It's definitely a bit on the lower side of things. It was definitely under budget, and we got somewhere around 1.93 tokens per second. Now let's see um, if we give 6 GBs of memory, and that should be able to fit the model in. It's 4.6 GBs. We changed nothing else. And this is my favorite part. I'm keeping the model identical, workload is identical, the contracts, threads, batches, everything remains the same. I'm changing exactly one number. And I'm not telling InfernoRT to change your strategy. I'm only telling it that there is more memory now available. So let's see what Inferno does with that. Now, straight away, it recognizes that now he's got a budget of 6 GBs, so he can go full resident. And so now we are using 4.64 GBs straight away. And immediately we can see things are much faster now. So Inferno RT has rejected the previously owned stream plan because that's not necessary anymore. It has proved that fully resident execution is legal because of the new budget, and it is automatically moved to the faster candidate. There is no fast mode. I didn't disable eviction. I didn't calculate how many layers to fit. I only changed one number. I changed one resource contract constraint, and the runtime reconsidered the complete execution plan for me. Um, and as you can see, it's much faster now. So the main takeaway from this is that the user does not choose an optimization mode. The runtime needs to be smart enough to choose the best mode that is available uh, based on your resource permit. So okay, so let's move on. Over here, we got a speed bump, definitely a 5x speed increase over there, and we got 4.36 for prompt token, and for decode token, we got 5, which is not bad, not bad. It could be better, it could be worse, but you are in charge of that. You get to choose how it's supposed to be, which is a good thing. All right, so let's move on. Now, what I want to show you is everything that I've shown you so far has been a GGUF model, and uh, there's one more thing that I wanted to show you. InfernoRT also has a working ONNX path. So if you are working with ONNX models, um, the command surface remains pretty much consistent. The model format basically is now ONNX, and the compute backend remains CPU. Nothing else really changes. And the ONNX execution provider is selected independently. So this separation is basically intentional. Um, so a model's storage format should not lock the developer into one execution environment, and we are so kind of democratizing the whole process. So let me show you how that command looks. This is kind of how it looks. It's fairly similar. Model path, that's wherever your ONNX models are. Model format, that needs to change from GGUF to ONNX. Tokenizer, that's a prerequisite for ONNX, so we are declaring that as a flag over here. Everything else, execution provider, temperature, prompt, everything else basically remains the same. So let's hit enter. We'll see how that looks. Um, okay, so we ask complete only the sentence, and then the problem is that the AI model is not a model. Yeah, so you'll get an inference, but your mileage might vary based on the models that you're using. Uh, the model that we are using is basically just a normal, non-standard um, ONNX model. It's just model. Um, so that's where we are at right now. So now, for the final act, basically, let's establish why the constrained execution path matters so much, right? And this is the same. Um, let me find something that can help us over here, right? Let's see if we can get something working. Uh, okay, yeah. Sorry, I had to pull in a new terminal over here. Um, so yeah. Uh, Now what I'm trying to do is I will try to run the same. It's basically everything's the same. We have the same model, we have the same thread, context, boundary, Llama CLI. Everything more or less remains the same. Now it uses 8 threads, 496 token contexts, and I'm applying a full gigabyte measured RSS boundary, and we'll see if that works. And yeah, so well, what happened there was, and we were using Llama CLI, um, is that Llama CPP is probably the best runtime that is on the market right now. And there are a lot of sections where Llama CPP is unbeatable. Um, so right now, the out of memory problem that is, it's a very highly optimized runtime for conventional inference. Um, and InfernoRT's priority here is completing the workload inside an explicit resource budget. And so that's why the comparison monitor terminated Llama when it crossed the 4 gigabits boundary. It did not complete the request inside that constraint. And InfernoRT faces the basic problems earlier, but instead of assuming full residency, it evaluated alternative execution candidates. And even before the inference began, it found a legal streaming strategy and completed the workload. And I'm not claiming that InfernoRT is currently faster than unrestricted Llama. The claim is that InfernoRT can execute this model within a resource boundary where the conventional fully resilient path cannot. And it's very important because a lot of people working on edge devices or working on different models and orchestration, just democratizing and bringing them all together, making it very easy to work with. I think that's what we're trying to provide here. Now everything you saw today ran locally and entirely on CPU. There was no cloud inference endpoint. There was no remote model. No GPU dependency. No manual layer configuration. Uh, and this is not where the work stops. This is where the work begins. We recently demonstrated a 70 billion parameter model running on a machine with 16 GBs of RAM using the same broader execution framework. That does not mean like a 70 billion model suddenly becomes, as fast as a small resident model. Of course not. It just means that a workload that normally requires far more memory can become executable on a dramatically smaller hardware. Um, we also now have a working Linux version that expands, potential surface beyond a Mac demonstration. Right now, we support dense models of the Llama family. We are working towards the Gemma models from Google, and we should be able to support them very soon. But because of our Linux enthusiasm and working Linux version, we can sort of test our runtime over edge servers, robotic systems, industrial machines, private infrastructure, sovereign deployments, things like that. Things where cloud access could be very expensive, could be unreliable, undesirable, or plain right out impossible. The most important part is there is not any single optimization. It is the fact that the developer should not have to reason manually about every layer, cache, residency tiers, execution candidates. The developer should just be able to say, here's my model, here's my workload, and here are the resources available. And the runtime decides how to use them. And so our goal with InfernoRT is simple: the most intelligence under the least resources. And we want developers to think about what their application should do and not spend their time working on whether the tensors will fit or not. The hardware provides the boundary, and InfernoRT finds the plan. Thank you.